Dear students, under the topic graph theory, here we have lecture 4. The theorem says that if delta, that is small delta, is greater than or equal to a positive integer k, then the graph G has a path of length k. So in order to prove this, first we should know what is this delta. This delta represents the minimum degree of the graph G. So the minimum degree of the graph G, which means that if you consider a vertex from the graph G, it will have at least degree delta. So, for example, if delta is equal to 4, there will be 4 vertices adjacent to that vertex in minimum. It can have more than 4 vertices, but minimally it will have 4. So, in a similar way, we are considering a graph G where the minimum degree delta is greater than or equal to k. So, it will have k vertices adjacent to it. That is, a vertex can have k vertices adjacent to it or more than that. But minimally, it will have k vertices adjacent to it. So, that is the meaning. So, if we consider a graph of that kind, then it will have a path of length k. That is, the number of edges of that path will be equal to k. So we shall prove this theorem. Usually first we will do the illustration and then we will look into the theoretical proof. But for this theorem, first we will do the theoretical proof and then I will give you the illustration. So now we will consider a graph G. And we will consider an arbitrary vertex V1 of this graph. So when we consider a vertex V1, which is an arbitrary vertex of this graph G, and since the minimum degree is greater than or equal to k, how about the degree of V1? It will be either k or greater than k. Because the minimum degree itself is greater than or equal to k, V1 can have minimum degree or it can be more than that. So the degree of V1 will be either greater or equal to k. And what does this imply? V1 is adjacent to at least k vertices. So the word at least means here that it can have k vertices adjacent to it or more than that. So V1 is adjacent to at least k vertices. Now we will consider another point V2 of this graph. And we will presume that V2 is adjacent to this V1. Because there are k vertices minimally adjacent to V1. So one of the vertex, let it be V2. So let V2 be the vertex which is adjacent to V1. In that case, we can say that there is a V1 V2 path in this graph G. So after this, and since V2 is a vertex of G, again its degree will be either k or greater than or equal to k. So degree of V2 will be greater than or equal to k. So what does this imply? Now V2 is adjacent to at least k vertices. Similarly, how we did for V1, in a similar way, since the degree of V2 is either greater or equal to k, it can have k vertices minimally adjacent to it. Or it can be more than k also, but minimally it will have k vertices adjacent to it. Now out of those k vertices, let V3 be one of the vertex. So let V3 be adjacent to V2. Like how we took V2 adjacent to V1, now we are taking V3 adjacent to V2. So this will imply there is a V2 V3 path. So V2 V3 path. Now combining, already we have V1 V2 path and now we have V2 V3 path. So combining these two, what we can say? We can say that there exists a V1 V2 V3 path. Now we keep on proceeding this process. So there is a V1 V2 V3 path. And as we keep on proceeding this process, what happens? We can generalize it. So we continue this process. So as we continue this process, we can write in general. So having chosen, now we are choosing vertices v1, v2, etc. up to vi, where this vi will be greater than or equal to 1 but lesser than or equal to the minimum degree delta. So there will exist a point. So there will exist a point. So what is that point? We will have a point vi plus 1, and that will be not equal to any of these points. So which will be not equal to v1, v2, etc. up to vi. And how this point will be? It will be such that this vi plus 1 will be adjacent to vi. So is adjacent to vi. So what does this have? What does now happen? This process will yield a path of length k. So this process yields a path of length k in this graph G. So therefore we have obtained a path of length k. So whenever we have the minimum degree to be greater than or equal to a positive integer k, then G has a path of length of that positive integer. So that is the theorem. So hence we have proved the theorem. So therefore G has a path of length k, and we took delta to be greater than or equal to k in this case. So hence we have proved. So I hope you would have understood the proof of this theorem. Thank you. Now here we have the illustration for this theorem. If you see the vertex v1, what is the degree? 1, 2, 3, 4. The degree of this vertex is 4. So here we have 1, 2, 3, 4. The degree is 4. And the degree of vertex v6 is 1, 2, 3. And here we have the degree of vertex v5. I have drawn this line. So it is 3 minimally. And what about the degree of vertex v4? 1, 2, 3, 4. So this is 4. So if you see here we have the degree as 1, 2, 3, 4. So all the vertices have degree at least 3 or more than 3. So if you see here the degree is at least 3, and here the degrees are 4, which is greater than 3 but not lesser than that. So we can say that the minimum degree delta is equal to 3. Now we have to check whether are we able to find a path of length 3. For example, now I am going to take a path here, that is from v1 to v2, and then from v2 to v6, and v6 to v4. So what is the length of this path? So from here v1 v2 we have one edge, from v2 to v6 we have an edge, v6 to v4 we have an edge. So the sum of the number of edges in this path is 3. So we see that we can find a path which is of length 3, and 3 is the minimum degree. So the value of k is 3 over here, and we are able to find a path of length 3. So therefore this theorem is satisfied for this graph. So this is the illustration. So kindly write this illustration for the given theorem. Thank you.